Welcome friends, let us today learn about the root locus technique using a simple approach on how to start understanding about the root locus technique. So in this lecture we shall focus on the following points. We will understand the root locus technique using a simple example in the beginning. Then we shall go into the different steps of the formulae to be used and applied on root locus technique. Then we will understand how the idea of variation of roots can be checked with the variation of different parameters like gain of the system. This is about the closed loop system. So by the end of this lecture we will understand how all these conceptions will lead to the definition of the root locus technique. So let us start with the simple example to make the concept. So the root locus concept, let me keep the heading the root locus concept. What is the root locus concept? So we can take an example of position control servo with the transfer function of the servo motor simplified to the second order system. So we can take the block of the transfer function of the servo. So let us define this as 1 divided by s into s plus 2. Then we have a power amplifier with a gain k. So we have a power amplifier with a gain k. Then we have the feedback. So here we will have a reference input to the system. So let us define it plus rs, and there is an error signal because of the error between the reference input and the output. So we are considering it as a position control servo with unity feedback to the system. So let us consider the negative unity feedback. So this is the power amplifier simplified. Then this is the servo motor and load, servo motor and load. So we can see that the open loop transfer function here is as simple as that. Open loop transfer function is as simple as k divided by s into s plus 2. So here naturally in the open loop system we have two poles. So poles of the open loop transfer function are at s1 equals to 0 and s2 equals to minus 2. So now if you find out the closed loop system, so the closed loop motor transfer function can be given as gs divided by 1 plus gs. So if we calculate it, it should come in the form k divided by s square plus 2s plus k. So we can go a little further to see how the characteristic equation of the closed loop system can be connected with the open loop system, and the variation of poles of the closed loop system will affect the variation of different parameters of the system. So in a simple example like this, we consider the variation of the gain of the system, that is the k. So let us see the characteristic equation qs. The characteristic equation qs equal to s square plus 2s plus k, as we all know. So here, if the value of k, if k is greater than 0, so naturally roots of qs are negative. That we will check exactly by mathematics after some time. So closed loop system is stable. Closed loop system is stable. So this can also be verified using the Root stability criterion. So let us check from this characteristic equation. This is the characteristic equation. From here we can find out. So this is a quadratic equation, so we can apply the very common formula for as square plus bs plus c equal to 0. The roots are minus b plus minus root b square minus 4ac by 2a. So using the same formula we can find out the roots of this characteristic equation as minus 1 plus minus root 1 minus 4k. You can take a pause and find it yourself, because this will be minus 2 plus minus root 4 minus 4k by 2, so that can be simplified to this form. So here let us start writing about the different range of values of k, so that it should be clear to us how the variation of k is impacting the roots and vice versa. So if k equals to 0, if k equal to 0, what will happen? Roots, if k equal to 0, then roots of the open loop system are same as the roots of closed loop system. So if you can find it, let us put and see what happens if k equal to 0. So here if k equal to 0, then s12 are equal to minus 1 plus 1 and minus 1 minus 1. So these two become 0 and minus 2 minus 2. So the roots of the open loop system are same as roots of the closed loop system. So now you will follow how with the variation of k the system characteristic of the closed loop system is varying from the open loop system. So if k is increased now, if k is increased and roots meet at k equal to 1, say, and roots meet at k equals to 1, then what will happen? What we will see in that case, that s12 s1, 2 equals to, because when k equals to 1, then the radical term will disappear, so both the values should be minus 1. So this is minus 1 minus 1, like that we can write. So once we plot it on the s-plane, we will see how the roots are moving actually. So let us go beyond k equal to 1. Say if we consider k is greater than 1, then the radical part has the value 1 minus k. So naturally if k increases beyond 1, the radical part will become negative, so it will have the complex part in the roots. So in that case, roots depart the real axis, because up to now all the values of the roots were real, so it was traveling on the real axis on the negative side. But once the value of k increases beyond 1, roots are imaginary, so now the roots have to leave the real axis. So I can write roots depart from the real axis and system is underdamped, and the system is underdamped. So naturally we can summarize this like the three situations. Therefore, when k equals to 0, then we have roots are negative, real and distinct, that is 0 and -2, real, negative, real and distinct. So this is the case of overdamped response, or there is a exponential delay. So we can say that case of overdamped. Now again, when k equals to 1, so the roots are equal. So in that case we can say that roots are equal, and this is the case of critically damped system. Now the third case, when k is greater than 1, we say that the root have the complex parts, imaginary parts. So roots are complex, so roots are now complex conjugate. Roots are complex conjugate. So as I already mentioned, this is the case of underdamped system. Underdamped. So let us go a little further to draw it on the S-plane. We'll see how the roots are traced. So we see that when the value of k is 1, in that case we have the real part fixed, and then the imaginary part changes or increases with increase of k. So that I can write in statement over here. So with k greater than 1, the real part that is -1 is fixed and imaginary part is increases, and imaginary part increases with increase in the value of k. So if you plan to draw the plot, we can draw it on the graph paper, or you can draw it in freehand also with care for the accuracy. So in the exam, depending upon the requirement of the problem, you have to attempt it. If there are exact numerical calculations based on the graph sheet, then you require to take a graph and draw it. And if you just need to draw the graph, explain how the things are happening, and you can use analytical method to calculate different values, then that much of accuracy of a graph paper may not be required. So let us draw it by freehand. So we are here doing everything in the negative real axis, so let us be adhering to the negative real axis, and there are no roots on the right side of the plot. So let us say that we have a value, this is the S-plane, this is the S-plane. So we have the sigma axis, and we have the j omega axis. We have the origin over here, then we have to do something with -1, then we have to something with -2. So let us plot the poles and zeros of the open loop system first, because when initially k equal to 0, then we have the poles of the open loop. First is this one at the origin, second is at -2. Then we shall go for the plot of the root of the characteristic equation. So how the roots are moving? So initially when k equal to 0, we are having the poles at 0 and -2. When the value of k increases, so gradually both the trajectories will meet at k equals to 1 on the negative real axis at -1. So let us make a move. So we are moving from -2 and we move towards the value -1. Here also we move towards the value -1, -1. So we can write here that k equal to 0. Here also k equal to 0 at -2. Then at -1 we have know that exactly k equal to 1. So from here it will depart and we have the complex conjugate roots and the real part fixed at -1. So it should be exactly the vertical line like this. So we have to mention by the arrow so that thing should be clear. So in this way we are moving. So once we start moving, the value of the imaginary part of the complex number increases on either side. So to understand certain parameters, so let us make the denominations. So the denominations is like at we have j1, here j1, and here we have -j1. Then we have the parameters of the roots of the characteristic equation. So let us write down the roots of the characteristic equation of a second order system. This is S12 equals to minus xi omega n plus minus omega n root 1 minus xi square. So in case of underdamped roots, so we place a j over here. So here we can see that the imaginary part of the root is given by this length. This length determines the imaginary part. So this length is omega n root 1 minus xi square, and the real part over here is the real part, this one is the real part over here. So this is minus xi omega n. So if we can get it, let us do some simple mathematics over here. So what is the simple mathematics we have taken? Let us take a triangle. This is the right triangle. So we have on the x-axis xi omega n and on the y-axis omega n root 1 minus xi square. So what is the value of this hypotenuse? Can you say? Take a pause, use the Pythagoras theorem, and you calculate it as omega n, right? So this square plus this square, then square root will give you the omega n. So what is the value of this theta? So let us see it for cos theta. So cos theta equal to xi omega n divided by omega n equals to xi. So we can find theta equals to cos inverse of xi, right? So with this knowledge, so let us proceed to obtain the value of k for different position of the trajectory drawn in this figure and the variation of the roots. So from here we can further proceed to say, in this case when I am saying that I have the system with characteristic equation whose value is say s square plus 2s plus k equal to 0. This is equivalent to s square plus 2 xi omega ns plus omega n square. Then we have the value of omega n square is equal to omega n square equal to k, which implies that omega n equals to square root of k. So the second term, let us compare it. If you see that 2 xi omega n equals to 2 implies that xi omega n equals to 1, implies that instead of omega n you place the value of omega n as root k. So xi root k equals to 1 implies that k equals to square root k equals to 1 by xi, implies that k equals to 1 by xi square. So let us go to the figure. In the figure, see, for this position when I have imaginary part as j1 and real part as -1, in that situation what should be the value of theta? So by magnitude both are 1. This is 1 by magnitude, this is also 1 by magnitude. So therefore very easily we can say that theta equals to 45 degree here, because tan theta equals to 1, so theta equals to 45 degree. So let us use this knowledge to obtain the value of xi for that value of the theta. So once I write that for real part at -1 and imaginary part at j1, we have tan theta equals to 1 implies that theta equals to 45 degree. So it means we have the value of xi equal to cos theta. This is equal to cos 45 means 1 by root 2. So xi equals to 1 by root 2. From here we can get the value of k equals to 1 divided by 1 by root 2 whole square equals to 2. So with this you can understand that the variation of the value of the roots of the closed loop system over the trajectory for a given system will give us the variation of different parameters of the system, including the gain of the system. So by this we can conclude upon the definition of the root locus technique as a root locus of a system is the plot of the roots of the system characteristic equation, that is the poles of the closed loop transfer function, as some parameters of the system is varied or vice versa. So let us write the definition in words. Definition is a root locus of a system is a plot of the roots of the system, of the roots of the system, characteristic equation, characteristic equation. So roots of the characteristic equation are the poles of the closed loop transfer function. These are the poles of the closed loop transfer function as some parameters of the system are varied. So gain of the system, that is the gain of the open loop system, as appearing in the characteristic equation, of the closed loop system can be varied to find the range of stability of the closed loop system. So from this plot we can understand that the root locus of a system is basically a locus that is derived starting from the poles and zeros of the open loop system to the entire range of variation of the poles and zeros of the system through a trajectory which will determine the variation of different parameters of the system, and we can find out the range of such parameters for which the closed loop system is stable. So we shall come up with the complete steps of designing a root locus for a given system in the coming lecture. For today's lecture, this is the all you have to learn. I am thankful to the textbook of Professor M. Gopal from IIT Delhi, whose text reference is maximum taken throughout the lectures, and the simplicity he has adopted in writing the textbook so that we can learn about the control systems as a whole in a simple way through the textbook. So you can make a reference of this textbook if you require so. Other two references books are by Shyam series by Professor Sanjay Mandal, and another book is by S. Hassan Saeed of Integral University Lucknow. These two books are also good textbooks and can be used as reference and also for referring the problems. I am thankful to the Windows base because Windows 10 provides inbuilt tools like Jukebox, then the Microsoft Whiteboard and Windows Video Editor. These tools come in free with Windows, and it has been used extensively to develop the learning material on this platform. So if you like this video, please go to the like button and click it. If you have not subscribed it so far, Please subscribe it so that if you set the bell icon for notification, you can keep on getting the notifications for all future updates and uploads. Friends, if you have any queries regarding this video or any of the other lectures, you can always send me queries to controlsystemsfaq@gmail.com. My students can send me queries through WhatsApp and ask me through my mobile number also. Thank you for your patient listening.